Good morning, this is lecture 31, module 5, matrix analysis of beams and grids. If you recall, we had finished the reduced element stiffness method in the last session, and today we will look at the application of flexibility method to solving beams. This is covered in the chapter on beams and grids in the book on advanced structural analysis. Of the three methods, now we look at the last one, the flexibility method, which you are already familiar with. The flexibility matrix for a prismatic beam element is something that you can easily derive from first principles. We have already done that, but to refresh your memory, you have 2 degrees of freedom, you have a simply supported beam, you apply one unit force at a time, F1 star equal to 1, you know the two end rotations, one will be L by 3 EI and at the other end it will be L by 6 EI. And it is important to note that at the other end you will get a direction which is opposite to the direction you get at the first end. So you have to put a minus sign when you write the stiffness matrix. When you do F2 star equal to 1, you get a picture like that, and it is easy to write down the flexibility matrix. Remember, this 2 by 2 reduced element stiffness matrix is 4 EI by L, 4 EI by L, 2 EI by L, 2 EI by L. It is going to be L by 3 EI, L by 3 EI minus L by 6 EI minus L by 6 EI. There is a minus sign that comes. For convenience, you can take out L by 6 EI outside the brackets, and so you will be left with 2 2 minus 1 minus 1. So remember this, it is very easy to remember, it is for a prismatic beam element. If the beam element is non-prismatic, if it is stepped or if it is tapered, you can still derive it from first principles. How will you derive it? Which method will you use to get these rotations? You can use conjugate beam method, very easy, but usually we do it for the prismatic element. Okay, so in the flexibility method you are already familiar with the transformations. Unlike the stiffness method, now we move in the anti-clockwise direction in this chart. First you have the elements flexibility matrix, which helps you get the element level displacements if you have the element level end forces, that is the F star matrix. Similarly, you have at the structure level. Now I have written here FA and DA, but for statically determinate structures you can just write F and D. Please note that if we are trying to avoid including the reactions in the end forces, if you want to include them, it is possible. We demonstrated this in an earlier class by including rigid links and relating the support reactions to internal forces in those rigid links, but we will avoid that for convenience. So just like you had FA and FR, DA and DR in stiffness methods, you will have in place of that, you will have FA and FX and DA and DX. Okay, that is a big difference. You will get the X only if the structure is over rigid, statically indeterminate. If the structure is statically indeterminate, there are no redundants, so you have only FA and DA. So that is shown here, FA and DA, and the basic force transformation is the TF matrix, which really tells you that if you give the loads on the structure, you can directly get the relevant internal forces at the element level by doing that TF transformation. You will find that this is based entirely on statics, entirely on equilibrium, there is no compatibility in this relationship, and it is a unique matrix. it is generally a square matrix which you can derive by applying unit load one at a time. We will demonstrate all that. We have done that for trusses, we will do it also for beams. And there is the contragradient principle which links D star to dA, that is the TF transpose matrix. What is the use of this matrix? Can you tell me? Where does it help us? In trusses, how did it help us? Lack of fit. If you have some initial displacements in a statically determinate just rigid structure, a truss, you can find out the joint displacements caused by these movements. There will be no stresses if it is statically determinate, and you are actually solving a geometry problem using the help of statics. This TF transpose matrix also establishes that while you ensure equilibrium in the structure, statically determinate structure, you are also, without your knowledge, simultaneously establishing compatibility. So you are, that is the other advantage. In beams, where do you anticipate using the TF transpose matrix?
Temperature loading of a segment.
Temperature loads we usually do not encounter in beams, and they will come in frames because you need the axial degree of freedom, unless you are talking of a differential temperature, a temperature gradient across the depth of the beam, which we will not consider for the time being. So you will encounter initial displacements when you have support movements at non-redundant coordinates. You have two types of support movements. You have support movements at redundant coordinates which will directly go into the dx vector, and you might have support movements at non-redundant locations. We have done problems like that. Those you have to somehow convert to their effects in the primary structure, and that is where you can use the TF transpose matrix. Okay. And the other transformations you are familiar with, once you have the element stiffness matrix, element flexibility matrix, you have the structure flexibility matrix by the standard transformation TF transpose F star TF. Okay, so the F star matrix for the beam, the continuous beam, will be a diagonal matrix, right, because it is an unassembled matrix, and each of those elements in that diagonal matrix will actually have a size of 2 by 2 because you have 2 degrees of freedom, and Fi star is given by L by 3I, L by 3I minus L by 6I minus L by 6EI minus L by 6EI. This part is very clear. Then you have the force transformation matrix. The TF matrix you can separate out into TFA and TFX in case the structure is statically indeterminate, and we can include the fixed end forces which we will be required to do if you have intermediate loads on the structure. So this is a little aberration in the stiffness, in the flexibility method, because we are forced to borrow concepts from the stiffness method to find the fixed end forces and then import that concept here, because there is no other way you can deal with intermediate loads. Okay, so we do that, and do not put the TF transpose there. We had that problem in reduced element stiffness method. You had to manually assemble the FFA and FFX vectors. We will demonstrate that, and so we can talk of a net force vector as we did in the stiffness method, Fa minus FFA and Fx minus FFX. The only change we are making is we did not have the X, we did not have redundance in the stiffness method. Instead we had reactions, we had R, that is the only difference. And you can, as I explained earlier, you can, in case you have initial displacements at non-redundant locations, you can use the transpose. Okay, so the structure flexibility matrix is given by this, the compatibility equations you have to spell out. And how do you solve for the unknown redundance? Will you use the first equation or the second equation? The second. This is again another difference with the stiffness method. In the stiffness method we use the first equation to get dA. Now we solve the second equation to get Fx, and we plug that into the first equation if required. Sometimes we are not interested in knowing the displacement, we just want the bending moment and shear force diagram to get the dA matrix. Okay, you can solve these equations, we have done this earlier, and the method follows this format. Let us now demonstrate with a few examples. Let us take the same example which we did earlier by the stiffness method. You have a non-prismatic fixed beam. What is the degree of indeterminacy? Well, strictly 3 if you include the axial force, but we are really not interested in the axial force. We want to draw the shear force and bending moment diagram, and for that limited purpose, I have explained this earlier, you can reduce it to 2. And what primary structure would you like? Yeah, cantilever is the easiest. So, and we normally have a preference, I do not know why, for fixity at the left end, but there is no need, you can fix it at the right end, but we will do that. Okay. So we will release at C, then the structure becomes statically determinate, and then we treat those two redundants as loads of unknown magnitude. That is the trick. Fx is also now treated as a load on the primary structure, but its magnitude is not known. Fa is known. Okay, so this becomes our primary structure, the global coordinates 1 and 2 at B. We will always number the redundant coordinates at the bottom of the list. So 3 and 4 will go to the redundant coordinates, and you should identify it. Fx is x1 and x2. x1 corresponds to F3. We will see later when you have to do the net forces, it is not exactly equal to F3, but at least it is aligned in the same direction as F3, and x2 is F4. Is it clear? And the compatibility equations needed to solve this, in this case you do not have any support settlements. So D3 which corresponds to x1 is 0, D4 which corresponds to x2 is 0. In case you have support settlements, in case support C settles by delta downwards, you will modify this as F3 equal to minus delta, sorry, D3 is equal to minus delta, and in case you have a rotational slip theta at C, you will suitably modify D4. The question is, supposing you have the support settlement at A, you can't do it in dx, you have to do it as an initial displacement. We will see that little later. Okay. You now need the element coordinates, which are just like what we did in the reduced element stiffness method. They look the same, 2 degree of freedom system, simply supported beams, right? And you need to follow a certain procedure. Procedure is find out the force transformation matrix, find out the fixed end forces, you have to generate this manually, find out the flexibility matrix at the element level, generate the stiffness flexibility matrix at the structure level, write down your compatibility equations appropriately, solve the second equation to find the unknown redundants, and if you wish you can find the displacements also by solving the first equation, otherwise do not do that. And in this case we are only interested in the shear force and bending moment diagram, and find the membrane forces directly by using the force transformation, where you have to put in the correct values of the net load vector. Okay. Joint displacements you can get also this way, dA directly. Okay. Now let us do this together. Can you write down for this example the force transformation matrix? Okay. You have to apply a unit load one at a time. Let me help you. You have to fill in this matrix which I have left blank there, right? There are only 2 elements. So F1 1 star, F1 2 star pertains to the end moments in the first element, and F2 1 star and F2 2 star pertain to the end moments in the second element. You have 4 coordinates, global coordinates, F1, F2, F3, F4. F3 and F4 corresponds to X1 and X2, right. So I have drawn 4 sketches. I have drawn actually the free bodies. You can draw the whole cantilever beam, apply a unit load at a time. So let us take the first case, okay, just draw the first one. We are now applying F1 equal to 1. You can clearly see in a cantilever, if you apply F1 equal to 1 at B, BC is not going to be affected because that is a free end. If you take a free body there, you will not have any forces there. So that is 0 0. How do you solve this one? What do you get? I am not, you will get, I will draw it, I will show you, these are your reactions, okay. So I am showing the reactions in a different color, okay. You will get a downward reaction at A of 1 kilonewton and you will get a moment of 1 into 10 kilonewton meter acting clockwise, right. So this is the complete analysis of a simple cantilever beam subject to a unit load F1 equal to 1, right. Now you have to fill in that first column in the TF matrix. How will you fill it? Just reel out those values. Minus 10, next 0, next, great, that is it. It is just as easy as the displacement transformation matrix. Now will you fill in the next one? Let us do the next one. Next one is pretty easy. You get pure bending. You just get one moment there. So can you tell me how to fill up the next column? Minus 1, plus 1, 0 0, great. Let us do the third one, okay. Third one, you are now applying a unit load at the free end of the cantilever, right. So what are the moments you will get? You can also draw the shears. They look like this, right. 1 into 10 is 10 kilonewton meter. That 10 kilonewton meter will act clockwise at B in BC and anti-clockwise at B in BA, because every action has an equal and opposite reaction, got it. But you can see clearly that it is a sagging moment for both, and the moment you get at A will be 1 into 20, that is 20 kilonewton meter acting clockwise. Is this easy? Now tell me how to fill the third column.
10, minus 10.
Minus 20, plus 10, minus 10, 0. You will find that, let us say I give you a 3-span beam, it will always follow this trend, minus, plus, minus, maybe plus or 0. And the last one is very easy, you get a uniform bending. How do you fill this up? Minus 1, plus 1, minus 1, plus 1, that is it, that is all. So you are comfortable with the TF matrix. We have partitioned it because F1 and F2 correspond to the active degrees of freedom, active coordinates, and F3 and F4 correspond to the redundant coordinates. So we put a subscript A and X, A for active, X for redundant. Is it clear? So you have got this matrix, and if someone were to give you F1, F2, F3, F4 or the net values, just plug it in and you will get all the end moments. Once you have got the end moments, you can find the vertical reactions, you can draw the shear force diagram, bending moment diagram, but remember this can handle only nodal loads. You also have to add the contribution of fixed end forces, for which we have to borrow ideas from the stiffness method. So let us do that next. Fixed end forces, these are very easy to calculate, we have done it for stiffness method. So you just have to copy those same diagrams for reduced elements. So I will not explain this, you can find the fixed end forces, write them in a vector form like this. F star F is in this case plus 125, minus 125, plus 83.33, minus 83.33. You can put kilonewton meter outside. Is this clear? This is exactly what we did in reduced element stiffness method, nothing new. Now you have to generate FFA and FFX. Can you do that? And you have to do it manually. you can't use the TF transpose. So you remember 1 and 2 are at B and 3 and 4 at C. So you have to get the vertical reactions. If you look at F1F, it is the sum of 50 and 50, is it not? So you have to see what adds up at 1. So you get 50 kilonewton here, you get 50 kilonewton here, they add up to the coordinate 1, and that is how you get 100 kilonewton here. At the coordinate 2 you have minus 125 and plus 83.33, they add up to get minus 41.67, is it clear? At the coordinate 3 you have plus 50 acting up and you have minus, it is very easy, just have to put together everything, all the contributions from all the elements, algebraically add up those numbers, you have got the fixed end force vector at the structure level, is it clear? We actually did this when we did the axial element, we did exactly the same thing. So it does not matter, you have a beam element, you have an axial element, you have a frame element, the philosophy is the same. Can I proceed? Okay. Now you need to get the net load vector, which is Fa minus FFA, Fx minus Ffx. Now you had a nodal load, if you look at the original problem, there was a 30 kilonewton meter acting clockwise at B in the original problem. That is a nodal moment that is going at B, it is not going to any of the two elements unless you are told that it is positioned to the left or right. So it is going to the center and it could be shared in any manner possible. So it is a nodal moment, and so your nodal force vector is 0 minus 30 and the x1 and x2 which you identified in the beginning, that is your nodal force vector. Then you had intermediate loads which caused you to get fixed end force vectors, which we just computed. You have to add that with a negative sign because you need to eliminate them, whatever you get you get. So you will get the unknowns x1 along with the fixed end forces that you, is it clear? Very simple, you have to write it in this form. This is what we call the net load vector, the net load vector, is it clear? Now what do we do next? Compatibility equations are very clear, that is dx is 0 in this case. Now before we do all that, how do we need something, what do we need? Well, we can draw a sketch to clarify what we are doing. What we wrote in that vector will actually be reflected in terms of these arrow marks, right. The net load vector I have just shown in arrow marks, there are 4 elements in that vector, 4 components in that vector, F1, F2, F3, F4 net, is it clear? So what is the next step? You have got the transformation matrix, you have got the fixed end forces, you have got the net loads, you are ready to solve the compatibility equation, but you need something, yeah, you need first, before structure you need the element and then you have to build. So we go to flexibility matrix. So the element flexibility matrix, what is the matrix for a prismatic element? Yeah, just so that your memory is okay, L by 6 EI the diagonal, both diagonals, and off diagonal will be minus, no, L by 3I at the diagonal and minus L by 6 EI off diagonal, that is it. So you do that, you can do it in one shot, you have got the F star matrix, is it clear? Just put the correct L is 10 meters for both the elements and the EI is 2 EI for the first element and just EI for the second element, and the off diagonal elements are 0, are null, is it clear? Very easy to do. So F star is there, TF you have got, and you get the structure flexibility. We will not waste time, we know how to multiply. So let us say we get the answer, right. Which you do first I do not care, whether you do F star TF first or TF transpose F star first, you do not need all those things unlike the stiffness method. So here finally you must get this answer and it must be right, it must be symmetric. Now which is the one you need to invert here? That in stiffness method we always looked at the top left hand corner, that was KAA, but in flexibility, because everything is upside down in flexibility, you have to look at the bottom right hand corner, that is Fxx, is it clear? So that is 2 by 2 because your degree of static indeterminacy was 2. Take it out, invert it also, be ready. Okay, inverting a 2 by 2 matrix very easy. You are now ready to handle any loads. In this problem they gave you some loads, you got the net load vector, okay, you use that. So you write down the equations clearly, you do not have any initial displacements, you do not have any support settlements, so you write it clearly and solve for x, you just expand it and I leave it you to do it, you get some answers. You have to do it systematically, okay, but do we need to explain these steps, or it is quite clear? It is clear, you need to practice on your own. You get x1 and x2 and you can see what it means. It means you have an upward vertical reaction at C 94.61, you have a clockwise moment at C, fixed end moment is 292.27. We got exactly the same answers in a completely different way when we did the conventional stiffness method, when we did the reduced element stiffness method. Is it clear? This is completely different method but giving you exactly the same answer. Okay, now last thing, you need to get the element level forces. Actually you do not need to do this, you got the free body, but since we are doing matrix methods we might as well do this the hard way, but you need not. You got the free body, you draw the bending moment diagram there itself. But let us just play this game, and if you take the FF star vector which you have got, the TFA TFX vector, and you put in the net values of F1, F2, F3, F4, you will get those answers, and you can also get the displacements if you want. You will get D1 and D2. Perhaps the D1 is useful because you know how much it will deflect, it is going down, and in actual practical problems you need to control deflections. Usually in fixed beams deflection is not a problem, but in simply supported and cantilever beams it can be a big problem. Okay, then you draw your diagrams, we have done this before, we will not waste time. Problem number 1, fixed beam, non-prismatic, we have solved. Clear? We will do another problem, continuous beam. This is the toughest problem you can get, in the sense got all kinds of complications. What is the first thing we will do? First we will simplify our work. So we will get rid of the overhang because it will unnecessarily bring in more coordinates. We don't want, we want to minimize our work, so you do that. But still, even after doing that, what is the degree of static indeterminacy? 3, right? Just think of the primary structure. What primary structure is most comfortable for you? Cantilever. So cantilever means 3 props you have to throw away, right? That is the easiest way to understand. But why should it be cantilever? We can make it simply supported. You can do anything you want, but let us do it the way we are comfortable with. We will make it into a cantilever. So NS equal 3, and let us choose a support reaction that B, C, D as a redundant. We will call them X1, X2 and X3. So this is the structure we are going to look at. We will quietly remove the overhang and bring it back when we draw the final bending moment diagram, and that 50 kilonewton meter now goes as a concentrated moment at the end D. Okay, how do we proceed now? Well, first global coordinates. Global coordinates, you have 6 of them here, that is the minimum you have, because you have 3 rotations on top, 1, 2, 3, and you have these 3 redundants 4, 5, 6. Is it clear? You can number them any way you want, but because we are following a, normally we would have put the vertical translation as 1 and the rotation as 2, but here this is flexibility method, we are biased to forces not to displacements, and we have said that all the redundants we put at the end of the list. Is it clear? So the redundants are 4, 5, 6, they have to go to the end of the list, and the active coordinates are 1, 2, 3. Is it clear? And straight away write down the nodal forces. You have only one nodal force, which one? F3. F3 is this constant moment, which is minus 50 kilonewton meter, write it down, and your Fx vector is x1, x2, x3. which is connected with F3, F4, F4, F5, F6. Clear? Write down, do the make the framework ready to do analysis. If two students choose different numbering systems, not a problem, you should still finally get the same shear force and bending moment diagram. The numbering, the naming can be different. Okay, so you also have support settlements here at the redundant coordinates. That is, you have D4 and D5 minus 0.005 and minus 0.020. I would like you to think of what you need to do. I am not going to solve it here, but that is something for you to worry about. Supposing I had a rotational slip theta A equal to 0.001 radian, how would you deal with it? So please note down, that is a question you will get in your examination. If in addition to this, just formulate the solution. If in addition to this, for choosing the same redundance, if I had a clockwise rotational slip at A of 0.001 radian, how would you solve the problem in addition to all the loads that you have? Okay, so think about it. We have done similar problems earlier, but I want you to figure it out yourself. Okay, okay, now you have 3 elements, 2 degrees of freedom per element. The spans are different, 8 meter, 6 meter, 6 meter, and the EI values are different, 4 EI, 3 EI and 2 EI. Okay, what is the first thing you need to do? Force transformation matrix, fixed end forces, you can do whichever you want first. So that is the first thing you need to do, either do this or this. Next, find out the flexibility matrix at the element level, find out the structure flexibility matrix, solve for the redundance, find the membrane forces, find the joint displacement, standard procedure. Fixed end forces, we did this in fact only yesterday, so this is easy, this is also easy. This, be careful, yesterday what was the difference? We drew the same things yesterday, but there was a big difference between yesterday and today. What's? No, that was a prop cantilever. Element 3, we took advantage of a reduced element stiffness matrix because of the hinge, and we had only a 1 by 1 matrix and it was 3I by L. We do not play those games in flexibility method. Flexibility method, it is always 2 by 2 element. Is it clear? So you have to arrest that degree of freedom, D. So it is a simple case of fixity at C and D, and so your fixed end forces is as you calculate here. This is what we did in the conventional stiffness method, where we did not take any shortcut. Is it clear? So that calculation is easy to do. 50 kilonewton meter you just keep aside, it does not come into your fixed end forces at all. Is it clear? You are handling it as a nodal load, you put it as F3 equal to minus 50, you handle that separately. Okay. So I hope you are familiar with these calculations. Then what do you do next? You put them all together in a vector form, it will look like this. If you compare this problem to yesterday's problem, this vector is identical except that last F3 star F vector, because last time it was having only one value and that value was different from these two because it dealt with a propped cantilever, remember? Okay. But we use these very values in the conventional stiffness method if you go back, but in the conventional stiffness method we also had a 4th element, that overhang, is it clear, which did not have any fixed end force vector. Okay, it is good to look at the same problem by all the methods, so you will be really thorough and you can pick and choose whichever method you want. Okay, what do you do next? You have to assemble the FFA and FFX vectors. Will you do that? With the help of this diagram, write down the FFA and the FFX vectors. Just have to add up, please do it so at least you know the steps and the procedure. Fill up the FFA and the FFX vectors. Can you tell me the 3 values in the FFA vector? You have 3 moments, I think. The first 3 have 3 moments and the next 3. So, are you getting these answers? In fact, the solution is shown there, what you have to add. You just have to algebraically add. Is this correct? You need explanation? Yes? Praveen? What's your doubt? Last one, you're talking about FFX? FFA. FFA, the last one is you have a clockwise fixed end moment here, 66.67, and nothing else. This is just, this you need not show here, this should be thrown away. So that's all you have, so and it's minus because it's clockwise. Is it clear? Actually I should not show this, but this is a carryover effect from the previous, it's already dealt with, that cantilever, that overhang is already dealt with. And I hope you are familiar with how to get FFX, it's also straightforward. Okay, now you are ready, you have got this, I have just copied that diagram. What do you now need to do? You need to get the net load vector, which is FA minus FFA, and you can also get FA minus FFX and keep it ready to solve your compatibility. Will you do that? Net load vector. When we say load vector on a primary structure, it also includes the unknown redundants. They also form part of the loads, but those loads are unknown loads because the redundants are not known. So it's a systematic method, foolproof method. You do it step by step, don't make any mistakes anywhere, you can't go wrong. Of course, we have not yet found out the force transformation matrix, we will do that in a minute. So, are you getting this? You got the FA vector 0 0 minus 50, you got the Fx vector x1 x2 x3, you have got FFA and you have got FFX, it is just algebraic addition, okay, no problem. Then what is nice to do next? Take a look at those in the diagram, you see how beautifully you have converted all those intermediate loads into equivalent joint loads. That is the power of matrix methods, and you get the same displacements at B, C, D, that is the basis of the equivalent. Is it clear? But there are some unknowns hanging around x1, x2, x3, and to get those x1, x2, x3, see this is a loading diagram which does not suggest that B, C and D can't move, in fact B, C and D will move, but the correct answer of x1, x2, x3 correspond to the reality that you know how much B, C and D will move. It is not 0 because you have a known support settlement at B and at C. So that is a value you have to forcibly impose and you will get the correct values of x1, x2, x3. Right, so let us do this, now you do it on your own. Please generate the force transformation matrix for this 3 element continuous beam. Very easy, the first one, I mean you have to repeat what we did last time, in fact all of them look alike. Will you draw, fill in the blanks there quickly. First one, second one, third one, they are all similar, right. While you do it, let me ask you a question. When we did this solution by the consistent deformation method, we did some extra work. What was the extra work we did? We had to draw the unit load bending moment diagrams M1, M2, M3 and so on, and we also had to draw the capital ML diagram due to the load. We are not doing any of that, okay. How are we avoiding finding the M1, M2, M3 diagrams here? We are doing actually the same work because in the force transformation matrix you are capturing the 2 end moments and you are assuming a linear variation between them. So you are capturing the same essence in a matrix formulation. So it is easy to calculate, you will get all this. So you will find the unit bending moment diagram, unit load bending moment diagrams will either be linearly varying or will be constant. If you are applying a unit moment, you get a constant moment in element 1. If you are applying a unit load force, you will get a linearly varying bending moment diagram. That is all automatically captured by F1 star and F2 star. That is so, you must connect what you are learning now with what you did earlier, but this is a blind powerful method of doing it. Can I proceed? If you plug in all these numbers, you will get that matrix which will look like this, okay. It is similar to what we did earlier. Earlier we had only 2 elements, now we have 3 elements, not much difference, okay. What do we do next? We got the TF matrix, the TFA and TFX. What is the next step? The flexibility matrix, yes. So earlier we had a 2 by 2, now we have a 3 by 3. By the way, when I say 3 by 3, it is actually 6 by 6, it is actually 6 by 6 because each of those elements has a 2 by 2 matrix. All you need to know is what is the length, what is the span, 8 meters in the first case, 6 meters in the second case, 6 meters in the third case. What is the EI value? 4 EI in the first case, 3 EI in the second case, 2 EI in the third case. That is all, just plug it in. So you got the F star, you got the TF, what do you do next? Get F, okay, do not even waste time, you get it. You get F and just check that it is symmetric, because that is, and the lower right hand corner holds a secret, that is your, and make it as precise as possible. That is why I put 4 decimal places there, I put 6 significant figures, because that is a fellow you need to invert. If you round off heavily there, the inverted matrix will get you some answers, but when you multiply it with this matrix, you will not get an identity matrix unless the accuracy is high. You are not doing it, the computer is doing it. So you can do it, you can do double precision if you wish, you will get very good results, okay. Please note, unlike the stiffness matrix, the flexibility matrix is not guaranteed to be well conditioned. It has been proved that in some cases, depending on the choice of redundants, it is reasonably well conditioned, but sometimes it can be ill conditioned. If it is ill conditioned, when you invert it, you will not get a good inverted matrix. When you check out the product of the inverted matrix and the original matrix, you will be in for big surprises. You will not get an identity matrix, you will get a full matrix with all kinds of numbers in it, and so your answers will be all wrong. This is one of the reasons why the flexibility method as a general method for large structures is not chosen. But stiffness method is guaranteed to give you a good solution. It is a robust method, it does not have any choice unless you do reduced element stiffness method, which the software programs do not do. They do conventional stiffness method. A statically determinate truss which has degree of static indeterminacy equal to 0 will be analyzed as a highly kinematically indeterminate structure. The computer will solve a 100 by 100 matrix, invert it successfully and give you the solution, which you could have solved manually in a minute. But you need to check. See, a good engineer will use whatever software is available, but as a tool, the engineer is the master and you must be able to check, because sometimes you get ridiculous solutions. So you can solve for this and get x, x1, x2, x3, and if these numbers look familiar to you, it is because we have done this problem about 2-3 times. And find the member end forces, just invoke those equations. Fixed end forces you have already got, TF matrix you have already got, the displacement, the net load vector you have already got. Just multiply and add, you get the final answers. What are those final answers? They are the end moments in the final end moments, including the fixed end force vectors in all the 3 element. Once you have that, if you draw the free body, you can get the vertical reactions. You also put in the external loads and you can draw the free bodies. You can also find the displacement if you want. Now in a problem like this, which displacement do you think will be of interest? This is a 3 span beam with an overhang. Which do you think will be interesting? The overhang part. You would like to know how much it went up, right? But you are not getting it here. So how do you deal with? Yeah, how do you find it out?
Get D3.
Get the rotation at
D3.
D and then multiply it by the
Length.
good. You guys are smart. So that is what you can do. You can find, knowing theta d, you should understand that the third displacement is theta d. You can just multiply by the span, you can get delta A. You can also get theta A because it is a rigid body movement, okay, except for that 50 kilonewton effect for which you have a standard formula. So you have to add that. You can do that and this is your final answer. We have done this before, so is it clear? So we have really covered a lot of ground, we have finished. Please note that we have actually finished the stiffness methods and the flexibility method. We did only 2 problems in flexibility because it is not really used much in practice, but we have studied all the methods exhaustively. Only one topic remains to be completed. What is that? Grids, which is very interesting, and in your assignment I have given you a grid problem. I will actually show you how to solve it, but you solve it on your own. Thank you.